So this is a short video on a property called uniform continuity. So recall that a function f from some domain A to Rd is continuous if it satisfies the following lengthy property that we've seen a few times before. For every point a, little a and big A, for every epsilon bigger than 0, there exists some delta depending on both epsilon and a, so that for all points b within delta of b, f of b is within epsilon of f of a. All right, so that's certainly a nice property, but it would be nicer if delta depended on fewer things, right? That would be a stronger condition. And so in particular, we sometimes want to think about the following type of condition. For all epsilon bigger than 0, there exists some delta depending only on epsilon, not on a, so that for all pairs of points a, b, in little b inside big A, if a and b are within delta of each other, f of a is within epsilon of f of b. Okay. So this is a stricter condition, and the difference here is that in this case we have to choose delta before a instead of choosing delta after a. Why do we want this? Well, we're going to see a bunch of reasons that this property is nice throughout the rest of the course, but there's one reason that's sort of easy to see if you're interested in using computers, which is that if a function f has this property, it's really easy to discretize f, that is, to come up with an approximation for f which only takes on finitely many or countably many values. So we can do it sort of the following way, right? We fix some epsilon, we fix the delta that was in the previous definition, and we define this piecewise constant function f hat delta to just be sort of what I've pictured here. For every point 0, you choose f hat of delta to be, well, f of 0, but on this whole interval from 0 to delta. And then on the interval from delta to 2 delta, f hat delta is the value of f of delta on the whole interval. The value of f hat delta on the interval 2 delta to 3 delta is just the value f of 2 delta. So it's this thing here, right? So you end up with this sort of piecewise blocky looking function. What's nice about that function is if you have this sort of second version of the property, then in fact f of x and f hat delta of x are close to each other for every point x. If you don't have this property, this thing is not going to be true. That is, your discretization is going to be bad for some values of x, which obviously isn't so nice. Okay. So unfortunately, right, there's a reason that we define continuity the way that we do, which is that most continuous functions fail this test. That is, most functions that have this property do not have this second property, this stronger property. So I'm just going to give a couple of examples which illustrate the main ways that a function can be continuous but fail to have this second property. So first of all, let's consider the function f of x is equal to just e to the x. So we know that that's continuous. And I want to check that the second property fails. So I'm going to fix some epsilon. In this case, I'm just going to choose epsilon is equal to 1. And in order to check that e to the x fails this property, we need to check that for every value of delta greater than 0, there exists a pair of points x and y, so that x and y are close, they're within delta, but f of x and f of y are not close, they're bigger than epsilon apart. So how do we do that? Well, you can sort of see what's happening, or at least guess what's happening if you look at a plot of e to the x, which looks sort of like that. And you'll notice that the further out to the right that you get, the faster e to the x grows. So that is, if I have this little displacement delta here, this displacement here is getting bigger and bigger as x gets larger. Okay, so if I have x and x plus delta, this displacement here from f of x to f of x plus delta is growing and growing. So what we're going to do is, when we choose delta, when we get delta to be small, we're going to choose a value of x that's very, very large. So in particular, of course, I did this pre-computation. When I choose some particular value of delta, which I'm going to assume for now is strictly less than 1, we're going to choose x is equal to delta inverse and y is equal to x plus delta. So we satisfy at least this part of the condition. And then we could just calculate f of x minus f of y is e to the x plus delta minus e to the x. Okay, so I factor, I get e to the x times e to the delta minus 1, and we know that e to the x is bigger than 1 plus x, and e to the delta is bigger than 1 plus delta, and so I end up with this bound here, and if I multiply that whole thing through, I get delta plus 1, which is strictly bigger than 1. Okay, so I satisfy this condition as well. All right, so that's sort of one example of a function that's continuous but doesn't have this second property. For the second example, I'm not going to go through the calculations, but it's not so difficult to do yourself, and it's probably a good exercise. I'm going to let f of x be 1 over x, but not on all of R, just on the domain from 0 to 1, the open interval. And I'm not going to go through the calculations, but I am going to tell you what you should be looking at. When you look at the plot of f of x equals 1 over x, you can see that as you get closer and closer to 0, the function is growing faster and faster and faster. And so the smaller delta is going to be the closer you're going to want to zoom in on this region close to 0 to find the violations of the property. Okay, great. So this second property has a name. It's called uniform continuity. And I'm going to repeat the property here. So the property is as follows. For every epsilon greater than 0, there exists some delta greater than 0 depending only on epsilon, so that for all pairs A and B within distance delta, f of A and f of B are within distance epsilon. Okay. So like I said, most continuous functions are not uniformly continuous, but it turns out that uniformly continuous functions of compact sets, continuous functions of compact sets are in fact uniformly continuous. So let's go back to these two bad examples just for a second to see what happened. In the first example, I had this function that was defined on all of R, so it was defined on an unbounded domain, and we could see that the problem happened as the value of x went up to infinity. And here we had a function that was defined on an open interval, not a compact set, and we could see that the bad thing happened as we got closer and closer to the boundary. And you can see, right, there would be no way to extend this f of x to be continuous on the associated compact set, the closed interval from 0 to 1. Okay, so these are the two bad things that happened in our example, and the theorem we're about to prove says that essentially these are the only bad things that can happen. This is the only way a function that's continuous can fail to be uniformly continuous. The proof is going to be somewhat reminiscent of some of the other proofs involving continuous functions in compact sets. We're going to build an open cover of our compact set where we actually have an element of the cover centered at every single point in the set, and then we're going to take some finite subcover of that. So in particular, what do we want to do? Well, we know that our function f is continuous, and so for every point x in A, there exists some delta depending on x, okay, also depending on epsilon, but I'm not going to emphasize that in the notation, so that for all y in A, if x minus y has norm less than 2 delta x, then f of x minus f of y has norm less than epsilon over 2. Okay, I threw in these factors of 2 here. You can see for yourself, though, that that's perfectly okay within the definition, right? I can choose my constants. Great. So that's going to give me my uniform cover. I'm going to define u sub x to be the ball of radius delta x around x. Then, of course, this complete collection is definitely an open cover, right? All of the elements of the collection are open balls, so obviously all of the sets are open. And then, of course, u sub x definitely contains x, and my index set is all of A. So certainly that collection of open sets covers all of A. All right, well, A is compact, so u sub x is a finite subcover, which I'll denote by this here. And I'll let delta be the smallest of the delta x's that are contained in that subcover. Sorry. All right, so what are we going to be doing with this finite subcover? Well, we can sort of see what's going on, right? We have our function f here. We have our finite subcover, which is floating around down at the bottom in the domain of the function. And what's going to happen is the following. If I have any pair x, y that are within distance delta of each other, right? So I have some point x there and some other point y over here, which is within distance delta. Well, definitely x is sitting in at least one part of the cover, right? I mean, it's a cover. So there exists some z in I so that x is within the ball of radius delta z around z, right? That's just what it means for me to have a cover. But by the triangle inequality, well, y is within distance delta of x, and x is within distance delta of z, and so y is sitting in the ball of radius delta z plus delta around z, and delta is less than delta z, so in fact y is sitting in the ball of radius 2 delta z around z. Okay, so what are we going to do? Well, by this property here, that is the sort of continuity assumption that we were making when we defined all of the deltas, we have the following. F of x minus f of y is less than, well, certainly by the triangle inequality, f of x minus f of z norm plus f of z minus f of y norm. And then both of these by star are less than epsilon over 2, and so the whole thing is less than epsilon. And now I claim that we're actually completely done. If you look at just the green text, or the text that's circled in green up here, And down here, you'll see that actually we have exactly the condition we wanted. For all pairs x and y in A, satisfying x minus y norm is less than delta, then we get this conclusion: the norm of f of x minus f of y is less than epsilon. Okay, so we have that, that this function is uniformly continuous. That's all for now. Thanks.